Hello everyone. Today we'll discuss the basics of the shear force and bending moment diagram of the uniform distributed load. So this is the one problem we are taking. The cantilever beam having this uniform distributed load over the span of this beam. So how to draw the shear force diagram and bending moment diagram for this particular problem? So for that, to draw this SFD and BMD, we have to consider some of the points which is very important. The important point is that here we discuss first to draw this for this particular uniform distributed load UDL. The shear force diagram will be linear, and or we can say that the inclined line. As earlier we have discussed in the point load conditions that the shear force diagram will be vertical line in case of point load, and no load condition it is a horizontal line. But in case of this uniform distributed load, the shear force diagram will be linear or inclined line, and the bending moment diagram for this particular uniform distributed load or UDL will be 2-degree parabola. So this will be the parabola. So this is very important point. Now we can solve this problem. So before to solve these things, first we draw this free body diagram. The free body diagram for this particular beam is here. This is cantilever beam, so RB, because this is B point, and RXP, and the moment will come that I am giving name MR. This moment will come, and the UDL is there, uniformly distributed load over a span. This can also be denoted by this type of, or plotted by this type of diagram. So here the W is there. This is W is nothing but the intensity of load. Here you can say, we can write W is nothing but intensity of load. This is called the intensity of load. This W Newton per meter means every meter this W intensity is there. This Newton per meter means every meter, each meter this W load is there up to length L. Suppose this is a length, so total length L, this intensity is distributed over this span. So this is the free body diagram for this particular problem. Now next we can write the equation of equilibrium. And so already we have discussed in the many lecture, in earlier lecture, the equation of equilibrium. So now summation of fx equal to 0. There is a no horizontal load is there except RAX, so RAX P point is 0. Then similarly the summation of Fy will be there. Fy means only the vertical force we will consider. So here the vertical force is RB, and this W which is acting over the length L. So here, because the vertical load in the shear force diagram, we are taking this downward load, we are taking positive when we move right to left, and upward we are taking negative. So W into this L, because this W, this intensity of the load is total up to the length L, so W into L, so total length L, we can multiply it, and minus RB is there, upward force, so that is equal to 0. So RB will be W into L. So the value of this reaction force RB will be W into L. Similarly moment we can take. So if you take moment, so this, the clockwise we are taking positive, anti-clockwise we are taking negative. So clockwise, when we are taking the moment, one thing is very important in this uniform distributed load, because this load when we are taking, so moment is nothing but force into perpendicular distance. So that force is there, this is W into the length L is there over this span, this total span L. But here one very important thing we have to consider while calculating this moment equation or bending moment diagram. If we calculate, we know that this is the uniform distributed load, the whole mass of this uniform distributed load act at the center. This is very important for this UDL case. So at the center, so centroid will be at the center, which is nothing but L by 2 distance. So this is L by 2 distance. Here also this is L by 2 distance. So the entire UDL length having this much mass, so which will act at the center of this body, and the center is nothing but at L by 2 distance. So this is very important, that also we have to consider when we calculate this moment. So W into L by 2, this is very important we are taking while calculating this moment. So since it is clockwise, we are taking positive, and this minus mr is there, which is anti-clockwise. So that mr value, this moment value, will be W into L by 2, L square divided by 2. So this is the moment value. Now this is very important. So the centroidal distance we have to take when we consider this moment only, not the shear force. Now calculate the shear force diagram for this particular problem. Calculation. When we calculate these things, so we can consider the section. This is our, suppose UDL is there, and here this is RB, this is RA, RX, B or MR is there. So now when we consider, we take any section, we cut the section. So this section XX I am taking up to distance X. When I move from right to left, so X I am taking 0 here, and X is L, length L is there. So X start from here 0 to length L. So I cut any section. Now we can calculate the shear force at particular section. Just I am taking this section as like this. So because this UDL tries to push this beam downward side, so the shear force will be upward side. So this is up to X distance, shear force is there. This is X distance. Now we can calculate the shear force, means only the vertical force we have to consider, and this is W Newton per meter at X distance. So the shear force, because the shear force downward we are taking, when we are moving right to left, downward force we are taking positive. So this W, which is at up to X length, positive, and minus Vx will be there equal to 0. So that Vx, shear force at X distance, it will be Wx. So this is very important. Now here I can calculate same thing. We know that here the Vx equal to Wx, so we know that Vx equal to Wx. So now when X equal to 0, then we can put Vx, which is 0, so that W into 0 is equal to 0. When X equal to 0, shear force will be 0. Similarly, when X equal to L, so here X equal to 0 means at particular this point the shear force will be 0, and similarly we can move here up to length L. So at length what will be the shear force? So at length, if you put here, so instead of this X we can put this L, and so at X distance, X equal to L distance, the shear force will be W into L at L distance. This is very important. Now based on that, we can draw the shear force diagram for this particular problem. Now we can draw the shear force diagram for this particular problem. So if you draw the shear force diagram, we take this span, this is the length of span, we denote as a X, and this side, this is the positive shear force, and this side, this is the negative shear force. Now here we can say that the shear force, if you calculate at A, here you can see at A here x equal to 0, so shear force is Vx equal to Wx, and at A x equal to 0 here, so shear force will be 0. So at particular at A the shear force will be 0 here. Then slowly if you move towards the point B, this intensity is a constant throughout the beam up to B. So here we can take x equal to L. If the distance is L, x equal to L, so if you put here Vx equal to Wx, so instead of this x, if you put L, so it will be W into L. So just before B it will be WL, so just before B, so WL, some value which increases, and it is a positive, so we are taking a positive. And we should know that, as we have discussed, in the case of UDL the shear force diagram will be linear or inclined line. So here we can draw the linear or inclined line just before B. So here this is the inclined line, this is WL, and at particular B, this is the A and this is B. It's particular B because the value of RB is nothing but W into L, RB. So here if you move from right to left, downward force will positive and upward force will negative. So this W into L, which moves throughout the beam as a WL, and at particular B where RB's reaction is there upward side, so the value of RB is WL. So here the throughout the beam is a WL, so WL minus WL, so that will be 0. So at B, particular B, the value will be 0 here, so it come back its original position at B as a 0. So this is the positive shear force diagram for this particular UDL problem acting on this cantilever beam. Now we can calculate the bending moment, calculation for the bending moment diagram. Now the calculation we start for this bending moment diagram. So bending moment diagram, calculation. Calculation for this bending moment diagram. So if you calculate the bending moment diagram for this particular problem, this is the problem. So if you take a small section, we cut at x distance. If you cut from the x distance, this is the UDL, this is the A point, and if you cut any section at x distance, the intensity is W per unit length, or W Newton per meter. This is the section we cut for this calculation of bending moment diagram. Now the bending moment at this x distance will be this W into x. We can calculate W into x into, we have to always take from the centroid. So the intensity act at centroid W is nothing but W that act at x by 2 distance. Means whenever we calculate this UDL on any beam, we have to take this W into total distance because it is unit per unit length. So this intensity act per unit length means in total length how much the intensity will be there, so that is W into x, and after that it act at the centroid of the beam. so that is the half distance of this x, so it takes x by 2 distance, so that also we have to take. And since because this beam, this UDL try to move down this beam, so the case will be like this, which is called hogging. So hogging, when we move right to left, take this moment as a negative, so that w into x square by 2. So always in the UDL case, we have to consider this w into x, means the intensity act on the total length x and the centroidal distance. This we have to take always when we calculate the UDL load calculation on any beam. So the w into x into centroidal distance, that is half of this x, so x by 2. And because that is hogging condition, and as per our this sign convention, when we move right to left this clockwise, or this hogging condition, we are taking negative. So this is the our bending moment value at x distance, that is minus w into x square by 2. So now when we calculate it at x equal to 0, so at a, here you can see that at a here, where the x equal to 0, then the bending moment will be so at x equal to 0, bending moment will be minus w into that x equal to 0 means 0 by 2, that is nothing but 0. So at x equal to 0, the bending moment will be 0. And when we move here at L distance, A to B, so x equal to L, the bending moment will be minus w into L square by 2 minus w L square by 2 we can write. So at particular L distance, the bending moment will be minus w into L square by 2, that is nothing but this minus w L square by 2. This is at L distance. So this is the value at L distance, and when x equal to 0, this is the value 0. So now based on that, how we can plot the bending moment diagram? To plot the bending moment diagram, here we draw this. So the bending moment will be that the shear force which we have drawn here, that is nothing but like this is a positive x span at x, and at b this is the WL. So it was the shear force diagram. Now similarly we draw the bending moment diagram, but here in this case, as we have discussed, that in the UDL case, bending moment diagram will be the parabola, that x square is nothing but parabola, but parabola may be here, this parabola may be either this type, parabola may be this type, or parabola may be this type, like this. So it is the case of concavity and convexity. So concavity or convexity. So this is concavity or convexity. So here among these two parabola diagram, which one is suitable for our calculation, that we can say from this calculation, if x equal to 0, the value is 0. Here you can see, we know that the shear force relationship with this intensity of load in the previous lecture already we have discussed. You can follow or you can see that lecture. That is nothing but rate of change of shear force with respect to x is nothing but intensity, that is load. So here the bending moment and the shear force relationship is dm by dx equal to the shear force, that is V, nothing but shear force. This is the relationship between the bending moment and shear force and the shear force and intensity of load. So if we can see here, the bending moment mx equal to minus w x equal x square by 2. If x equal to 0, so bending moment will be 0. If x equal to 0, we know that mx equal to minus wx square by 2. If x equal to 0, bending moment 0. And in this diagram you can see that the bending moment 0 means is a parallel to the axis, parallel to axis. But it's parallel to axis means this, here you can see that this is the parallel to axis. But in the second case it increases, it is not parallel to axis. This first case is a parallel to axis. Now similarly, if you put x equal to L, so that will be minus WL square by 2. So it is increasing. So this bending moment, if you calculate, this is increasing here, but this case, first case, it is increasing continuously, while the second case it increases and then decreases. So among these two diagram, this first one is suitable. So we draw this bending moment diagram here at like this. This is the curve parabola which is parallel. So at A this is 0, and just before B it is minus WL square by 2, and at particular B again it's a 0, because this minus WL square by 2 and this plus and this minus will be 0. So here this is the negative bending moment diagram. So this is the all about how to calculate the shear force diagram and bending moment diagram for the particular UDL load on the cantilever beam. So thank you.